Okay. All right. Well, welcome back to those of you who were with us last time, and welcome if you're just joining us for the first time. So in this second lecture, I want to talk about some first calculations, but let me remind you where we were last time, or let you know some of the notation that I'm using if you're just joining us. So throughout this, the group is going to be C2, the cyclic group of order 2. And there are two kinds of orbits, so two kinds of orbit cells here. So I've got C2 across a disk, which means, oops, instead of pointing, I'm erasing. Okay, I've got these two cells and the action is swapping them. And then a point across a disk is just a disk with a fixed action. Remember our orbit category, orb C2. So it had our two orbits, C2, which is C2 mod the trivial subgroup, and C2 mod C2, a point, and the collapse map between them. And then C2 acts on itself via what I'll call T for the twist. And we talked a little bit about what a Mackey-functor would look like in this setting. So we have some values on each of the orbits and some values on the maps as well. And the coefficient system part told us we should have these contravariant maps, but then the Mackey-functor altogether also has these weird covariant maps. But anyway, we saw a diagram kind of like this. So our contravariant maps also called the restriction, and these other ones called the transfer. But we're mostly going to focus on this Mackey-functor constant F2, so F2 underline, and this just puts F2 at each spot. That's what I mean by constant. You put the same thing at each orbit, and we'll have all our contravariant maps be the identity, and then everything else is forced. So in this case, that makes the covariant map 0. Okay, so this is the closest equivariant analog of working with coefficients in F2, which non-equivariantly is usually like a pretty easy place to compute, right? F2 is a field. But as we've already seen, things are a little bit more complicated equivariantly, and I'll remind you of some of that. Okay, so some other notation. We've got our representations. So there's the trivial and the sign representation. And so I'm gonna take a bunch of copies of both of those and call that an RPQ, where I'm using that motivic grading. So P is the dimension and Q is the weight or twisted dimension. And then when I 1-point compactify one of those, I get SPQ, so my representation spheres. And we looked at some examples of that last time. So here are those same pictures again. S22, two copies of the sign representation gave us that rotating sphere, for example. Okay, so because we have those two irreducible real representations, we've got a bi-graded theory for our ROC2 graded cohomology. And so my notation for that is just HPQ of X in whatever coefficients will work in constant F2 coefficients, as I said. And since we're gonna work in that the whole time, I'm just gonna drop the coefficients. So upshot, we've got this bi-graded equivariant cohomology theory. X here is some C2 space, and we want to be able to compute what this cohomology theory does to these equivariant spaces. Okay, we also talked a little bit about how this bi-graded ROC2 graded cohomology extends Bourdon cohomology. So Bourdon is just going to be the part in there that corresponds to trivial representations. So I've got weight 0 here. And what we do to get from that to the ROC2 graded is, well, maybe many things, but one of the things we talked about is that the difference here is we allow for the suspension isomorphism with respect to representation spheres. So if I smash X with a representation sphere, I would shift these indices appropriately. Okay, and some of those have non-trivial weights, right? So of course that's going to take me out of Bourdon cohomology. But okay, great. So that's most of our setup. And the nice thing about Bourdon cohomology is that it's very concrete. I know how to compute it. You just build a C2 CW structure. You apply your Mackey-functor or coefficient system. You don't need a Mackey-functor for that. And then you take homology. And we'll do some examples of that. But we already looked at some very small examples, right? We said, okay, we could compute Bourdon cohomology of a point. Well, that's got a pretty easy cell structure. C2 also got a pretty easy cell structure, one equivariant cell. And we applied the Mackey-functor and we got just an F2 in degree 0 and nothing else. But when we look at the whole ROC2 graded picture, there's a lot more. So this was M2, our, maybe let me leave that part. Okay, so this was M2, our ROC2 graded cohomology of a point in constant F2 coefficients. And we said this is an infinite dimensional commutative non-Noetherian ring. Okay, and that's a little bit scary because I don't know about you, but in algebra I studied modules over Noetherian rings mostly. And so this is going to take us into some weird algebraic stuff, but that's okay. We'll be able to handle it. So let me tell you a little bit more about this picture. I think I said some things last time, but maybe not the complete story. So what do I have here? I'm drawing this bi-graded picture so that I've got P, my dimension, on the horizontal, and my weight is drawn vertically. I've got these two cones, and every dot inside the cones, every lattice point really represents a copy of F2. So all of these dots are a bunch of F2s, and they go on forever, so that's how this is infinite dimensional. What else? This top cone is polynomial in tau and rho. So I've got tau squared. Here I have rho tau, which is also tau rho, since it's commutative, rho squared, rho cubed, so on, forever. There's a little bit of a gap here, and theta is in weight -2, by degree 0 -2. And theta is infinitely divisible by rho and tau, meaning not that tau or rho are invertible, but if I took this class and I multiplied by tau, I would get theta. So theta over tau times tau is theta. That's what that notation means. Let me also tell you that, and make this thing jump around. That's probably going to happen a bunch. So now this thing's a little finicky. It'll help if I move it. Okay, so this is M2, cohomology of a point. And we can see for degree reasons that tau times theta is the same as rho times theta is 0. So all I'm saying is tau has weight 1 right here. And if I multiply this by tau, I'd land in this gap, and there's nothing there. And the same if I multiplied by rho. Okay, so rho has by degree 1, 1, which is going to take me into this empty space. Okay, so that's easy for degree reasons. Not as obvious for degree reasons, but still true, you can calculate, is that theta squared is 0. And I say that's not immediately obvious just because theta has weight -2, theta squared would land here. So it could have been theta over tau squared, but it's not. What else? Oh, I wanted to remind you that this is extending Bredon. So the Bredon cohomology, which we explicitly computed, just sits here on the p-axis. Okay, so the ROC2 graded picture is much more involved, much richer, has lots of extra structure. And this is kind of a giant thing. And I don't know, when I first met it, I think it felt a little bit scary also. But the biggest question that I get asked when I talk about this work is why? How do you compute this? What is this thing? Well, unfortunately, to tell you that whole story would take longer than this mini course, I suspect. But let me at least give you a hint about how we would get started and get some practice with these things. And then I'll give you some references to look at. Okay, so let me say that this is due to unpublished work of Stong, which is maybe one of the challenges in figuring this out, is that you can't just go and look it up. Or at least not the original source, but oops. Let me at least tell you how to start computing. Okay, so we actually already began the computation, right? We did the weight 0 part, and we did that last time. So if you look at star comma 0 of a point, well, anytime you're in weight 0, you're looking at trivial representations. That's just Bredon cohomology. So you build a C2 CW structure for a point. That's pretty easy. You apply your Mackey functor, compute cohomology. So that wasn't bad. Okay, why is there all of this extra stuff? Well, let's start to try to see what this might look like, and we'll look at Q equals -1. So I'm down here and expecting to find nothing, right? I have this gap. Okay, well, how would I go about computing this? I'm looking at H star minus 1. So I'm going to kind of compute this by weight. I've got H star minus 1 of a point. And it's easier to compute things, or it's easier to use the suspension isomorphism if I'm working reduced. So let's go ahead and give that a disjoint base point and make this reduced. And if I had a point with a disjoint base point, I might as well call that S0, just the 2 points trivial action. Okay, and if you like, I could call it S0, 0, but there's kind of only one S0. Okay, now I want to use the suspension isomorphism, and my goal here really is, okay, maybe I should have said this at the outset. I basically only know how to compute Bourdon cohomology, right? That's all we've talked about. And then suddenly there's this ROC2 graded picture, but we only know explicitly what to do for Bourdon. That's where we build the cell structure. So I want to try to make this Bourdon cohomology, and I'm going to do that by using the suspension isomorphism. Well, I'd like it to end up in weight 0. So I'm going to smash this with a sphere. Let's smash it with S11. S0 smashed with S11 is just S11. And so then I'll get, I'll shift the indices by 1, 1. Oh, and that 1 plus minus 1 is 0. That was the whole point. Okay. And I see Dan made a comment that yes, there are other ways to compute this. So there's a slick computation Behrens and Shah have using the R motivic cohomology of a point. So that's another way to get there. Okay, so I've used the suspension isomorphism, and now I've smashed my way up to weight 0 so that this is Bourdon cohomology, and now I can compute it. Oh, but it's Bourdon cohomology of S11. So I got to build a cell structure for S11. That was part of your homework. And then apply the Mackey functor and compute the homology. Okay, so let's go ahead and do that. What does S11 look like? Well, S11 was this reflecting circle. Oops. Right, I 1 point compactify the sign representation. So I've got this reflection action. And so I see, okay, well, I could start with these 2 fixed points. Let's make that point disjoint union point. And then I would want to attach on the one cell, or maybe many one cells, to get this reflecting circle, right? Well, I'm just going to do that with an equivariant one cell, so C2 cross D1. And that's got this swapping action. And if I glue that on by taking these ends and crushing that, crushing that to a point, that's my P map from C2 to a point, and I'll do the same thing here, then I formed S11. Do we believe it? Okay, cool. Great. So that's my cell structure. I noticed that I want here to have reduced cohomology of S11. So I actually want to work reduced, and I need to pick a base point. I didn't really say when I wrote this down, but usually we make the base point the point in infinity. It doesn't really matter in this picture, so I'm just going to cross out one of these points because we want to work reduced. We could compute the whole thing unreduced first and then reduce later, but I might as well save myself the trouble. Okay, so let's write down the chain complex, or the cochain complex, I guess, that's reduced for S11. Well, we should apply whatever Mackey functor to a point in degree 0, and we should apply our Mackey functor to this equivariant cell in degree 1, and that's a C2, okay? Okay, and then what is the map between them? Well, I look at what is the attaching map. So my attaching map, maybe let me remind you, this is degree 0 and degree 1. So my attaching map here was this P map on the boundary. So I should get P upper star. Okay, I don't really need to do all this, but I'm kind of trying to show you how you might do this in other coefficient systems. But we're of course working in the constant F2 coefficient system or Mackey functor. So I'll put F2s in both spots. And then what was our P upper star? Well, all of our contravariant maps were sent to the identity. So just an F2 to an F2 connected by the identity. And then I take homology. So the reduced homology of S11 is, well, that kills everything. I just get 0 and 0. Okay, and maybe let me remind you in our picture of M2. Whoa, and scroll wildly, sorry about that. This thing's really jumpy today, apparently. So I'm just gonna draw the outline out of laziness, but we had something that looked kind of like this, right? And there was that little gap. And what we've just computed is, oh yeah, there's nothing. Whoops. Come on. We just computed, nothing goes there, right? Just all zeros. Okay, great. On to the next. Partly I want to convince you that yes, there should be stuff off the Redon cohomology, that there should be extra stuff in the ROC2 grading. And now all I've done is show you that there's nothing. So let me try to show you a place where you actually see something, right? Let's look at weight -2. So that's where theta lives. So we should get something. Okay, well, we're gonna play basically the same game. So I'm gonna look at the whole weight 2 line, H star -2 of a point, and I'd rather work reduced so I can use my suspension isomorphism. So let's give it a disjoint base point, make it S0. Then let's use that suspension isomorphism to somehow get to something we know how to compute. Well, the only thing I know how to compute is Redon, so I better get to weight 0. So I'm gonna smash with something that has weight 2, and the only actual sphere I know like that is S22, so let's make this like that. Okay, so I smash S0 with S22 and I just get S22, and that adds 2, 2 to the bi degree. And so here I am, star plus 2, 0. But moral of the story, Redon cohomology of S22 is going to tell me about this weight -2 part of M2. Okay, so now we're up to Redon. And we know what to do there. We build a cell structure. And again, this was homework. So notice, by the way, that S11 includes into S22 as a meridian. So I'm just going to build on from what we had. Let's actually just copy this rather than draw it again. Okay, and now try to figure out what else we need. Okay, so I feel like this is kind of a strange forum to do this, but normally I would ask the audience, like, what should I do here? But hopefully you've already figured it out. I'm gonna need an equivariant 2 cell. Not to say that this is the only cell structure I could use, but I think this is gonna end up being a minimal one. So I'm gonna take a C2 cross D2. And what do I wanna do? I just wanna sew those along the boundary. So I wanna take one of these disks and put it on that circle. I've got my circle and I slap the disk on. And then I want it to be an equivariant one so that when I do that, the other one goes on the other side and they're swapping. And that gives me that rotating action. Okay, so that's precisely what I wanna do. I have to think a little bit about how to attach that. And so maybe let me say, sometimes it helps to think about orientations here. Like when I think about this S11, it was swapping directly over, right? It wasn't like an antipodal thing where it twisted or something. So I kind of had this orientation on my C2 cross D1. And all I'm trying to say is I kind of have those 2 D1s that are really one equivariant cell, C2 cross D1, have the same orientation. So when I attach this 2 cell, this equivariant 2 cell, I need to like go around the boundary of this thing and figure out how to attach it here. And I want to do exactly what I just drew. So as I go around the boundary, I should go all the way around the circle. And because of that covariance, that'll just force the other one to attach on the other side. Okay, so what does that look like? Well, this was a C2 cross D1, and this is a C2 cross S1 on its boundary, right? There's the boundary. So I just want to like attach one of the things, I want to attach this to one of the parts of C2 and to the other. I don't think I'm making any sense. Let me write down what the answer is, and then maybe I can make more sense out of it. All I'm trying to say is I should go around for the one copy and then backwards along the other copy to go all the way around the circle. Maybe that makes more sense. Okay, so I have those same cells. Let me take my old cell picture. That was to build S11. I needed all that stuff. And now I also need a C2 cross D2. And I was just trying to work out like what should the attaching map be on its boundary. And let me not try to draw that because it'll be a mess, but let's write what we got. So we're trying to build this reduced Quotient complex for S22. And notice I still have that same crossed out base point, stick with the same base point. So this is reduced, and I've got my 0 cell, so I should apply my Mackey functor to that. I've got my equivariant 1 cell, I would apply my Mackey functor to that, and now I've got an equivariant 2 cell, so I apply the Mackey functor to that. And we already saw this was attached by a P, so it was P upper star. And that whole maybe kind of messy story that I was just trying to tell is how do I attach this other piece? Well, what I want to do is id minus twist. So I'm just saying this is a map from a C2 to a C2 kind of thing. And I could think of this as like my trivial copy and my trivial copy, and this is my other copy and my other copy. As I go around this, I should hit the trivial copy and then the other copy backwards. So that's id minus twist. Okay, so now I actually want to do that in the constant F2 Mackey functor. That gives me 1 here as before, and then 1 minus 1, which is just 0. Maybe let me write that. And so I compute homology. Well, there's still no homology there, but now I get that F2 there. And that is precisely the thing that we were expecting, because when we look at M2, now we've just computed, let me try to get a different color. So now we've just computed this line, and that's where theta lives. So we just put a 0, and an F2. Okay, that's a mess of a picture, so let me erase that. But okay, so moral of the story, there are some non-zero things off the p-axis, and you could slowly compute them. This is sort of complicated. Dan pointed out, by the way, that you actually know that this map has to be 0 because this should be a chain complex, right? So, sorry, I don't know if you can see where I'm pointing. You know that this has to be 0 because it should be a chain complex. So we could have figured that out in kind of an easier way, but the reason I went through all of this is, you know, maybe you want to do this computation in some other coefficients. Now you know how to get started, at least. All right, well, we could see that this is going to take us a long time, but we could continue in this way. You can kind of imagine how S and N would go, and that would give you the weight N. There's a lot more stuff to say here, so this won't get you the whole story, but I'll just say and continue and offer you a place that you could look. So my favorite reference from this approach is it's going to end up being not in F2 coefficients, but in constant Z coefficients. But this is written nicely in an appendix, and it's appendix B, and it's specifically of the archive version, so not the published version. But this is Duggar's paper that I think is called, Anatia Herzenberg. Spectral sequence. For KR theory. Okay, I can send you a copy if you send me an email. All right, so that was all sort of a complicated piece, and I saw Richard asked if there's a good reference for the multiplication structure. So really what we will have done if we continued in this way, we would have only gotten the groups in the bottom half of the plane. Then you span your Whitehead duality to get the groups in the top, and then you need to compute the ring structure. And Duggar's appendix describes how to get the ring structure. So yes, look there. And David asked, this is a chain complex of Mackey functors, should the F2s be underlined? And the truth is they could be, so you could compute this as Mackey functor valued. And I think that, that's what Stong's original computations looked like. That's what a lot of people's computations look like. So what I've been writing here is only the point side of the Mackey functor valued bigraded cohomology of a point. This is just really half of the data, but that's enough. So that's sort of enough to capture all of the information here in the special case of C2. So I think it's easier to work without all the Mackey functors. Things are complicated enough. And when you just have a bunch of F2s on the page, it's much easier to do these computations, as we'll see in a few minutes. So that's partly why I'm preferring not to do that. But yes, you're right. We could do this all Mackey functor valued. And if you want to work in other groups, you may want to. Though I still think even the point side is interesting in other groups. Okay, so all of this, we were using this cell structure to compute Bourdon cohomology, and I just want to let you know that in the constant Mackey functor, at least, you can skip some of that. So this fact that if you wanted HP0, so the Bourdon cohomology in constant F2 coefficients, then that's actually just isomorphic to the singular cohomology of the quotient in F2 coefficients. Okay, and this actually works for any constant Mackey functor and really any group, but you do need constant coefficients. Otherwise, it's not really clear what you should put here as your singular coefficients. Well, let's just check. We could have done this all much easier. We could have said, okay, what's S11 mod C2? Well, we had that picture. I wonder if I still have it in the memory. Nope. We had that picture of this swapping circle. Okay, and if I look at the quotient, I just fold those two pieces on each other and I get an interval and it's contractible. So the quotient is contractible. Oh yeah, there shouldn't have been any reduced cohomology there. And if I look at S22 mod C2, well, that was my rotating sphere. Oops. Keep trying to use the fancy tools they have built in, but I'm not really that fancy. Okay. So I have this rotating sphere. If I want to think about the quotient, then I only really need half of it because the other half is that C2 applied to it, right? Or the C2 action applied to that. So I just have half of it. I just have this disk. But then what does the quotient do? It's going to sew that piece back to itself. So this is going to be an S2. Okay, maybe that takes some thinking through, but yes, we saw the cohomology, the reduced cohomology of S2 right here. So it does check out. Okay, so nice. That would have gotten us there faster, but I wanted to tell you how you might compute other things and maybe in other Mackey functors. But all of that is looking, right now I think things are looking pretty tedious, right? We worked really hard just to get like these two little lines. There are three little lines of this giant thing, and it feels like we haven't gotten very far. So what I want to do now is say, we can just take M2, now that we know it, now that Stong has computed it for us, we can take M2 and now we can start to run with the computation. So really that was kind of the hard part to get us started, but now we can do a lot. And I see someone asked, what if you have a twist on those spheres, like antipodal action, the computation goes the same or something different that comes up? Well, so then you either build the cell structure or you compute the cohomology of the quotient. Yeah, same deal. Those just don't show up, right? We didn't build suspension isomorphisms with respect to those spheres into our theory. So I only needed representation spheres to do this particular computation. Okay, so now that we have M2, or we believe that someone has made it for us and we could continue that computation, let's use it. Okay, so how do I want to use it? Well, I think I said this last time, but let's just make it really explicit, that there's always an equivariant map from X to a point. You can just crush your space. And so the map back on cohomology makes the bigraded cohomology of X an M2 module. Okay, well, module over a non-Noetherian ring. So maybe that doesn't necessarily tell me anything wonderful, but at least I can use M2 to some degree. Remember, we had that suspension isomorphism. So as soon as we know the cohomology of a point, we actually now know the cohomology of any representation sphere. So the suspension isomorphism tells us this should just shift things. So this is the reduced cohomology of a representation sphere is just the shift of M2. So if it's an SPQ, you shift by PQ. And what do I mean by that? Well, again, I'm at this point only drawing the outlines, but it means I've got something maybe like this. So that looks like I just drew S22, the cohomology of S22. But maybe let's label, normally this would be some P and some Q. Okay, so you just take that whole picture and shift it. Now again, there's really all those dots inside and all the tau and rho connections and theta and everything is there, but I'm being lazy and just drawing the outline. But great, we already know the cohomologies of all the representation spheres just like that, right? It really was just built into the computation of M2. Okay, someone asked last time about the ROC2 graded cohomology of C2, and especially like how that compared to the little computation we had done. So now what do we get for the cohomology of C2? Well, this is just going to look like this. So we knew at weight 0 what we should have, but we didn't know off that p-axis, right? Because that was leaving the world of Redon, and we just have this, a bunch of dots concentrated on the q-axis. So here's q, and p as usual, right? I'm setting up these pictures the same way as normal. So we could describe this as F2 adjoin tau and tau inverse. That's what I mean by that vertical line. Those are multiplications by tau. Now, of course, tau inverse isn't really a thing, right? That didn't exist in M2. So I'm describing this as an M2 module. Let's write that down. But tau was that thing that, you know, was just above 1. It had weight 0 or by degree 0, 1. So all I'm trying to say is that there are tau multiplications here and here and here and here and here, right? So tau inverse doesn't exactly exist, but every single thing here you can multiply by tau to get up to the next thing. In fact, if you wanted to compute this as a ring, maybe you shouldn't name it tau, but you would get essentially the same thing. All right, I had a whole lecture planned where I told you how to do that computation, and it was more than a whole lecture long, so I'm gonna hold off on that one. But technically, that you use this computation to compute the ring structure of M2. So that's gonna show up if you go back and look at that reference. Okay, so here's a couple M2 modules. We wanna compute the cohomology of other spaces as M2 modules. And another thing that we were asked about last time was the Pupa sequence. And we'll use that. So there's a Pupa sequence as usual. And you can just work it out geometrically, what it needs to look like. So if you had some map between equivariant spaces, you could take the cofiber right? Just y mod x if it's a nice, good inclusion. And then how should this continue? Well, I should write suspension of x and suspension of y and so on, right? But what kind of suspension is that? Well, that suspension, if you just think through the cone construction, is actually a trivial suspension. So you just smash with a trivial circle. Okay, and I'll leave that as an exercise. But the point is that in the usual way, if you have some cofiber sequence, then you get a long exact sequence in reduced cohomology. Okay, really, when I say that we have this ROC2 graded cohomology, I mean that we have a good cohomology theory. It satisfies all of the good axioms, right? So, of course, we should have long exact sequences. Okay, so what does that look like? Well, the Pupa sequence tells us really, I mean, another way to get that is to hom from the Pupa sequence to, say, our Eilenberg-MacLean spectrum or Eilenberg-MacLean spaces or something, right? And so that tells me kind of how this should go. And I say that because, you know, at first it's maybe not obvious with the bigrading how that should fit into the sequence. But, okay, so I want to go backwards. So I have like HPQ of X receives a map from HPQ of Y receives a map from HPQ of the cofiber, right? And then what I'm trying to say is, you know, how do we know where this should go? We definitely know it should go to the cohomology of the cofiber, but I see that, oh yeah, I should just go up 1 degree in the first, just in dimension, not in weight, and that's because of this Pupa sequence. So, okay, could play around with that a little bit, but moral of the story, we have this nice long exact sequence, and it's really a long exact sequence for each weight Q. So that Pupa sequence didn't really see the weight. Okay, but because it came from this Pupa sequence, from these geometric objects, from these nice maps of spaces, all of these maps are M2 module maps, right? They have to respect the structure that we have. So I can assemble these. And I can think of, let's see, I want to name this one my differential, my connecting homomorphism. So I have all of these together, and I could just think of this as something from the reduced cohomology of X to the reduced cohomology of the cofiber. But notice that I should go up 1 degree in dimension. Okay, and then someone asked, does that mean we have a Z's worth of long exact sequences, 1 for each Q? Yep, absolutely. And now what I'm doing is say, take all of those long exact sequences, well, they all have maps between them, right? There's like taus and rhos and thetas that connect them, and just shove them all together. So I've got this one sequence, and now it's all a long exact sequence of M2 modules. Okay, and anytime you have a long exact sequence, you get a short exact sequence. So this is just an exercise in homological algebra. Use the first isomorphism theorem, and you'll see that the co-kernel of this map includes into the reduced cohomology of Y. Okay, what was Y? Y was the thing in the middle here, right? In the middle of our cofiber sequence. Maybe I should even underline the cofiber sequence I'm thinking of. Okay, and so then I've got this maps to the kernel. Okay, so what have we learned from all of this? If we had some cofiber sequence, the cohomology of Y is just an extension of the co-kernel of the differential, the connecting homomorphism, by the kernel, right? So this is a way we could compute the cohomology. Great. Okay, so let's do an example where we know the answer as a little bit of a sanity check to try to put together all of the things that I've been saying, and specifically to make this make sense in the pictures. So let's look at the reduced cohomology of S11. well, that's a representation sphere. So I know by the suspension isomorphism, I should just shift my M2 to start in by degree 1, 1. Okay, but let's do a sanity check and see that kind of happen from knowing M2 and the stuff about co-fiber sequences and long stack sequences. All right, so what would that look like? Well, I need to come up with a co-fiber sequence that involves S11. And the way I did this, I put my middle of the co-fiber sequence in the middle of this sequence. So I'm going to try to get S11 in the middle. So let's try to include something into S11 where we also know that we have a nice quotient. Okay, well, there's this classic co-fiber sequence involving S11 where S11, remember, looked like this circle with our reflection action. Okay, and then I could think of S00 or S0 as just those fixed points, including as the origin and the point at infinity. Yes, okay. This, by the way, is called rho because it really is rho in a very geometric sense. Now, we have rho as this element in by degree 1, 1 in the cohomology of a point, but we can think of that as a map, and it comes from a map of spheres, and it's this map of spheres. So it's aptly named rho. Okay, so then I quotient, and I squish this thing down, and I'm going to end up with this like 2 swapping loops, right, with a single fixed point. And we've actually seen this kind of picture before. So this is C2 plus smash S10. And this is our co-fiber sequence. Okay, well, I said we saw pictures like this before. I was talking about the Pontryagin-Thom collapse map, and that's exactly the kind of thing that I've done here. But I want to make sure that we're all really on the same page. So let's go through the geometry of this explicitly. So this is C2 plus smash S10, and let's remember what smash means. So I should take the product, and I should mod out by the wedge. Okay, and what is the wedge equivariantly? Well, I really mean kind of have to unpack what all of this old non-equivariant stuff meant. So I really mean take the first thing, cross the base point of the second, together with the base point of the first thing, cross the second thing. Okay, so let's be really explicit about this. Right now I'm just trying to convince you that this picture that I labeled C2 plus smash S10 really is C2 plus smash S10. Okay, and then maybe just to remind you where we're going, because now I'm deep in this thing, we will have had this co-fiber sequence with S11 in the middle, and we will be trying to compute its cohomology and see that we really get a shift of M2. But before we do that, let's look at the product and then quotient by the wedge. So I've got C2 plus C2 with the disjoint base point. That's really just 3 points, but these two are swapping and that other one's fixed. And then I've got S10, well, that's just a circle and it's all fixed. Okay, and so if I cross them, well, I should have a circle there. These are going to be very sloppy circles. And then a circle there, right? But these ones are swapping. Okay, well now I want to quotient by the wedge. And what is the wedge inside here? Well, I should take, the reason I wrote this out explicitly is that like I don't immediately see a wedge somehow. This looks like these disjoint things, but it's not, because C2 plus cross a point is part of the wedge, and the base point of that cross, oops, sorry, that shouldn't have been a union, that should be a cross. The point cross S10 is the other piece. Okay, so I should, for C2 cross the base point, I need to pick like a base point of S10. Any point will do, so let's take that. And this is telling me you should crush C2 cross that base point. So all of that stuff should get shoved together. And then the next piece, the base point cross S10, that's telling me you should crush the copy of S10 corresponding to the base point. Okay, now do you see the butterfly thing? I call it a butterfly. Okay, so I've got this point got smooshed together, and I have these sort of two loops, and they're swapping, and I said I call this the butterfly, and I'm claiming this is C2 plus smash S10. Well, we just computed or built it really explicitly as that. Let me just point out that when you do that, what I'm saying is that this point under the action goes to this point, and so over here, you know, that point goes to that point. They're sort of like isomorphic copies of S1 being mapped together. But you could just twist this thing and get a similar picture. And this plays a role in the computation of the cohomology of C2. And I just think it's a fun fact. Whoa. So I could make this C2 plus smash S11, and these would be isomorphic spaces. Just twist this thing. And that would mean this point should go and then swap. Right, so I use the diagonal action on the product. So that would tell me switch copies and then do the flip over. So anyway, I just thought that was kind of a fun geometric fact. Those are the same. I partly say that so that when I write this, you don't have to worry like, oh, wait, which circle are you really smashing with? Should we be careful? No, we don't need to be careful. Okay, whew, that all took longer to say than I expected, but let's see how it goes. So what are we trying to do? We're trying to use this co-fiber sequence that we've built here to compute the cohomology of the middle, and then probably have to solve some sort of extension problem like this, right? Use the long exact sequence, get the short exact sequence with an extension problem. So let's look at that long exact sequence. Well, I'm gonna draw it. It's much easier to draw than it is to actually write down. And our differential should go from the reduced cohomology of S0. That was this guy. Oops, I want to make that a different color. Okay, and then the connecting homomorphism should wrap around to a shift of the cohomology of that guy. So let's maybe do green. And the whole point of that whole argument we just did is just to convince you that, yeah, this flapping butterfly thing really is C2 plus smash S10. It was named appropriately. Okay, but now we know the cohomologies of these things. So this is just M2, and this should be a shift of the cohomology of C2, right? We took C2 and we smashed it with a representation sphere. So this is, I guess I haven't named that. Let's just call it the reduced cohomology of C2 plus, just to be consistent. Okay, so let's draw that picture. Okay, so I've got an M2 starting in degree 0, 0, and I'm being lazy and only drawing the outline, but remember there's a bunch of stuff in those two cones, taus and rhos and thetas and all of that. And then I draw this other one, that's just a single vertical line, really just a bunch of dots stacked along a line, all of those tau connections. Okay, and the differential goes from the red to the green. Oh, sorry, that was a poor choice. Okay. Let me make it blue. Sorry, I know some people are red, green, colorblind, and then this picture won't make any sense. Okay. Mapping from the red to the blue. All right, so this is a map out of an M2, right? And M2 is a free module. Oh, goodness. Okay, so M2 is a free M2 module. Not a lot to say there, really by definition. Okay, so, but the point is this differential is determined by D on the generator. Okay, so let's maybe name that generator X just to have some name, and let's name the class over here Y just to have a name. And so there's a question, there's this differential. What is d of x? And we see from degree reasons, this might have been a mess if we've written out actually the explicit long exact sequence algebraically, right? But drawing the picture, I can see it's possible that d of x is y. Okay, so now there's a question. Okay. Oh, and I see there's also a question in the chat, unrelated. So isn't this shift here? So I'm going to ask you to, someone asked about how this shift should work, and I'm going to ask you to play with those indices and see that, yes, this is correct. There's no problem here. Okay, so there's this question, is d of x equal to y? Do we have a zero differential? Do we have a non-zero differential? And how could we figure it out? Well, that p-axis, that's Berdan cohomology, right? We could compute the Berdan cohomology of this thing by building a cell structure. Or you could use the cohomology of the quotient, right? That gave us a really fast way to get there. So, well, the p-axis is Berdan. But we also know it's the reduced singular cohomology of the quotient of the thing we're after. Remember, this was all to compute the cohomology of S11, which we already know. We're supposed to get an M2 out of this story somehow. But this thing's contractible, as we already computed, so that should all be zero. Yep, so yes, d of x is equal to y. Okay, and now that tells you actually a lot of things. That also tells you that d of tau times x is tau times d of x is tau times y, right? These are M2 module maps. That tells me that I could put a row multiplication in there and pull that out. Okay, and I could put a theta in there. I don't know if you can read that. And pull that out. Okay, well, there's infinitely many elements of M2, right? So this is going to take me a long time if I want to work it out this way. But the whole advantage of the picture is that I can just see it. So here's tau times x. Maybe let me even write it. Here's tau squared times x, and it's going to hit tau times y and tau squared times y. So I immediately know that I have those differentials also. I'm calling D the differential. So I know those maps. And do I have to worry about rho times x hitting something? Well, no, there's just nothing there, right? So this over here, rho times y, this is just zero for degree reasons. There was nothing over there. Do I have to worry about theta hitting? Well, turns out theta times y is zero. That thing just had a single strip, and I guess I need to tell you that theta times it is zero, but you can see here that tau kills this. So if that hit, tau wouldn't kill that, and I'd have zero mapping to something non-zero. That would be bad. Okay, so my point is you don't want to write out all of this stuff. You just want to use the picture to compute. And how does that go? Well, I see that this whole line here should hit this line here, and then nothing else happens. The module structure is kind of just built into the picture. And so now I'm going to draw what's left. Okay, so I hit a lot of that blue tower, but not all of it. I'm left with this part. Oh, no, that's not true. I'm left with this part, right? I should have nothing on the p-axis. That was the whole point. And then what part of the red am I left with? Well, I've got this lower cone stuff, and then once I get to rho, all of that stuff survived. Okay, now again, really there's dots inside these cones. I'm only drawing the outlines, but the point of this computation is that here we have the kernel, the blue was the co-kernel, and now we have an extension problem. This is supposed to fit into a short exact sequence with the cohomology of S11 in the middle. And it doesn't really look like the right thing, right? What are we supposed to get here? We're supposed to have a shift of M2. And it sort of looks like a broken M2. If you ever heard me talk about my work specifically on this structure theorem, then you've heard me say this term, broken M2. This is what I mean. It almost has the shape of M2, but it's broken. There's no obvious row connections here, for example. There's no obvious reason this should have been 1. It was like really row bar or something, right? It came from row. But we know the answer. So there have to be these row connections. There has to be a way to connect this up and make this an M2. Okay, so the point of this story is that we can use these pictures to do these long algebraic computations in a much easier way. It takes a little getting used to, and we'll work with some more pictures so that I can convince you this really is easier. But okay, so the pictures are really helpful, and B, and this cohomology as M2 modules is kind of weird, right? We have all of these complicated M2 modules that could show up along the way, and then we have these extension problems to solve. And I don't know if this is fair to say, but I think it is, that usually those extensions are non-trivial. In this case, we saw there had to be some kind of non-trivial thing to get these row connections to connect these two pieces. Okay. I'm trying to figure out if I have time to do one more example, and I think maybe we can start it, but we won't necessarily finish. So far, we've only used this to compute something we already knew, and maybe that's a little disappointing. So let me at least start to compute something we don't already know. Someone asked a little bit about the antipodal spheres, right? So let's look at the cohomology of S1 antipodal. And I'm going to make that with a disjoint base point and take reduced cohomology just so that I can fit it into nice long exact sequences and not worry about that. Okay, so this has the antipodal action. And I know that if I take S1 with the antipodal action and I quotient by C2, that's like RP1, right? So this is an S1. Okay, so I immediately know that if I looked at the cohomology, I should have F2s there. Let's just say this is the cohomology of S1 antipodal. But then there's the question of, do we have stuff off the p-axis, right? Okay, well, the usual game here is to find a cofiber sequence, fit this S1 antipodal in the middle, run the long exact sequence in cohomology using the pictures, and then maybe you have to solve some extension problems. So how could I do this? Well, S1 antipodal has a free action, so I can really only include a free thing, and if it's going to be smaller, it's probably basically C2. Okay, I'm trying to make this all work out to be pointed so that I'm working in the reduced case. So all I mean here is that this disjoint base point will go to this disjoint base point. I can almost ignore them. So I've got C2 includes into S1 antipodal and quotients to, does anybody know? No, it's too weird of a setting. Okay, well, I've got 2 points including into my circle and I crush them together. Oh, that's our butterfly, right? So that's C2 plus smash S1. And I don't care what kind of S1 it is. It's the same, right? They're all the same. Okay, so there's our cofiber sequence. It helps to have some colors here. So let's give them some colors. And let's run the long exact sequence. That should have the connecting homomorphism wrap around between these and shift up 1 degree. I should have said that's part of why I'm drawing it horizontally, because of the degree. And of course, I'm writing this wrong. +1. Okay, and now we can draw that picture. Well, those are just cohomologies of C2s, and one of them is shifted. So I've got the cohomology of C2 that lives right on the Q axis, and then I have a shifted copy that lives at degree 1, and now maybe there's this differential. Oh no. This differential between them. But I know on the P axis, they better not, right? If there was a differential, this whole line would just come and kill the other line because of all the tau connections. So I know that can't happen because I need to have those 2 dots left. And so this differential is 0. And that makes this the kernel and the co-kernel. And now there's an extension problem. Yeah, let's go ahead and be consistent. Okay, and as I said, most of the things that happen here, we're going to have a non-trivial extension. And we're out of time, so I won't tell you how that works this time, but I'll probably start with that next time. But what's going to happen is we'll see that they're actually row connections. Again, row is giving us those non-trivial extensions. And so we have this kind of whole strip thing. Oh, I'm already over time. I'm sorry about that. Let me stop there.
Okay, great. Well, we're going to thank